All right, hi, chemistry class. Hope you're doing well. It's Mr. Irving coming at you from my new home in Southern California, where we have absolutely no furniture, which is why we have a terrible echo. I'm just going to apologize in advance for the low quality of this video. But I wanted to make this for you because the next topic we're going to be talking about is rather complicated, and I wanted to make sure that you were prepared. So you just finished a do now where you were looking at percent composition, right? And started off talking about a pizza that you ordered for dinner, and you consumed 2 of the 8 slices. What fraction did you consume? That's 2 out of 8 or 1 out of 4. What is this fraction in percent form? Well, you just grab your calculator, 1 divided by 4 times 100, right? And so the key thing here with percent composition, and if you don't understand this, you're going to have a hard time with today, so feel free to pause the video and ask questions. The idea here is that what we're looking at is the part over the whole times 100, right? This gives us our percent composition. And this idea applies to everything that you do, absolutely everything. So think about your test grades, for instance. When you receive those, how are they calculated? They're calculated by taking the part that you got correct over what you could have gotten correct, or the whole, times 100, and that gives you your great, 85%, or whatever it is that you get, right? This is percent composition. And so you looked at calcium hydroxide, and because you guys are excellent at naming compounds and writing formulas, you know that calcium hydroxide is Ca parentheses OH2, calcium hydroxide. And you're supposed to list the number of moles of each element. Okay, so, gosh, that ding was me. I've got to turn my phone off. Bad, Mr. Irving. Shouldn't have your phone in class. Okay, so you're supposed to list the number of moles of each element above, and the molar mass of each element. So let's assume here that we have 1 mole of calcium hydroxide. In 1 mole of calcium hydroxide, how many moles of calcium do I have? You should have gotten 1 mole of calcium. How many moles of hydroxide, of oxygen and hydrogen individually? Well, for every 1 mole of calcium hydroxide, we're going to have 2 moles of oxygen and 2 moles of hydrogen. What this means for us is that when we get a chemical equation, a chemical formula, the chemical formula is giving us a ratio. It's a whole number ratio of the atoms in that compound. And so just like I could say, for every dozen of these, there's going to be a dozen calcium and 2 dozen oxygen and 2 dozen hydrogen. I can say for every ream, remember a ream is 500, of calcium hydroxide, there's 500, or 1 ream of calcium, 2 reams of oxygen, and 2 reams of hydrogen, right? So what we're going to be talking about today depends on these 2 concepts here, the percent composition as the part over the whole times 100, and this whole number ratio of the atoms in that compound. Great. If there are any questions, let's go ahead and pause the video and ask those questions now. Okay, I'm going to go ahead and assume that there are no questions or that the questions have been answered, and we're just going to go ahead and we're going to move on to the next concept here. In order to be successful in this next part, you're going to need a couple of things. I need you to pull out a calculator, which hopefully you should already have, and I need you to go ahead and pull out your periodic table. You'll need that, of course. You'll likely need those two things every single day for the rest of the year, so might as well just bring them and have them available. Great. So I want you to imagine that a scientist discovers a new organic compound. He's discovering this compound in a tree. And so what he does is he extracts this compound and he lights it on fire. And when he does that, he's going to get a certain amount of carbon dioxide in the water. As you may know, whenever you burn something, you get carbon dioxide in the water. And he can take, based on that information, the amount of carbon dioxide and the amount of water produced, he can take that and determine whole number ratios, or better yet, percentages of carbon in the whole sample. What's the percentage of carbon? What's the percentage of oxygen? What's the percentage of hydrogen? And we get these in what are called mass percent. So I'm going to write this down, and you might want to do that too. A mass percent. Now, typically, a mass percent is going to be the weight of one substance, the mass of one substance, mass of substance 1, divided by the total mass, T for total, times 100. So when you have two things mixed together, like let's say I've got a little beaker, and in this beaker I've got some iron, and I also have some gold. Now gold is bigger than iron, so I'm drawing those a little bit larger. Oh, that might be a little hard to see. Is this too small? Let me do this. Okay. I'll try to write bigger so that you can see better. So if I were to take, say, okay, what's the mass percent of gold here? I would take the mass of just the gold, the mass of one thing, divided by the total mass and multiply it by 100. And when I do this, I get what's called a mass percent. A mass percent is a certain kind of concentration. Concentration. And we're going to talk about concentrations a little bit at the end of this unit, so you don't have to worry about them too much right now, but we're just introducing you to this idea. Now, if you think of something like acids, right? And you may have heard in some kind of TV show or movie or just, around the house, oh, that's very concentrated. Well, what do we mean by that? Well, colloquially, hard to get that word out. Colloquially, what we mean by that is there's a high amount of that particular substance in the total amount of substance. So if I have, say, highly concentrated hydrochloric acid, that means that there's a lot of hydrochloric acid usually dissolved in water, right? So in the ratio of one to the other, we would say that the ratio of the substance over the total is going to be quite high, right? So if you had very low hydrochloric acid and were feeling a little crazy, you could dump it all over your body and nothing would happen. But if you had very high concentrated hydrochloric acid and you dumped it on your body, it would burn your skin away. That's not great. For those of you who were prone to acne as I was in middle school, you might have used a salicylic acid facial cleanser, right? And it will say on the side there that the concentration of salicylic acid is usually around 12%, right? And the idea there is that it would dry out your face, dissolve those oils for you, so that you would be less prone to get acne. For those of you who go and get hydrogen peroxide, right, on the side of the hydrogen peroxide, it'll say hydrogen peroxide 3%. That means that 3% of that is hydrogen peroxide and the rest is water, or even rubbing alcohol. Usually it'll say 70% alcohol on the bottle, or 91% alcohol. Right? These are concentrations. Today we're going to be really, really interested, though, in this mass percent. This is just one of many ways of articulating concentration. And what this does is this can give us ratios in the form of a percentage, so they're not whole numbers, unfortunately, of different kinds of substances. Now, when we do that, we can get what's called an empirical formula. Okay, so you're going to want to write this down too. I'm going to write this bigger here for us. Empirical. I got to double check that spelling. Empirical formula. Yes. And I want you to think of empirical formulae as a representation of the ratio of atoms to one another. So for instance, if I had glucose, C6H12O6, and I wanted to write, this is the chemical formula, right? And I wanted to write the empirical formula, it would be the ratio of these atoms to one another, simplified, right? So the idea of an empirical formula is simplification. So if I were to simplify this, right, I would get 1 to 2 to 1. And that would be CH2O. So this is the chemical formula here, and this is the empirical formula. Great, I wrote that a little bit bigger. Hopefully that's a little easier to see. Okay, so remember the name of the game for empirical formulae is simplification. Now this is as opposed to the molecular formula. And the molecular formula is going to be the actual ratio, the ratio in fact. And so if this here is the empirical formula, then the molecular formula is C6H12O6. Do you see that distinction there? Simplification for the empirical formula, but then you're going to have a certain number that you can multiply this ratio by. In this case, it's 6. And this multiplied in gives you your molecular formula. Now, your question at this point is probably something along the lines of, Mr. Irving, why the heck do I need to know this? What is the point here? What's going on? I don't understand why we need to know this. And that's a good impulse to have right now. I just want you to bear with me for a minute. And I want you to turn to the practice problems for empirical and molecular formulas, which your sub should have printed out for you. Right. The very first question there talks about vitamin C. So let's go ahead and pause the video, make sure everybody has a copy of this, and make sure you have your calculator and your periodic table out. All right, let's go. Again, sorry for that, that echo. It's pretty gnarly, but we're doing what we can. Okay, so ascorbic acid, also known as vitamin C, is 40.92% carbon. 40.92% carbon. It's 4.58% hydrogen. And it is 54.50% oxygen. And these are mass percents, right? So this is telling us, oh, we're a little out of focus. the best we can do. Okay, so this is telling us here that we have a certain ratio of mass in a sample of ascorbic acid. And this wants us to calculate the empirical formula. Okay, how are we going to do that? Well, here's a confounder. Carbon, hydrogen, and oxygen, they all weigh differently, right? If you look at your periodic table here, we can see hydrogen, wonderful, wonderful hydrogen, has a molar mass of 1.01. That means that in its nucleus, there's going to be, on average, 1 particle. And if you look over at carbon, you'll notice that its mass is 12.01. In this case, that's atomic mass units or grams per mole. And so looking at this, we know that the average nucleus has 12 particles or so. Here for oxygen, 16.00, we know that it has 16 particles, give or take, on average. Okay, so oxygen is 16 times greater than hydrogen in mass. So if this is 16 times greater than this, then we know that there's 1 atom of this for every 1 atom of that. But that's so complicated because I don't have whole numbers. I'm not very good at doing mental math here. So what are we going to do? Well, if your first thought was, wow, Mr. Irving has been telling us to practice moles for 3 days straight and I'm bored out of my mind about it, maybe this has something to do with moles, you'd be right. You'd be right. So here's how we're going to tackle these problems. If we want to get the empirical formula, EMP, I spelled it wrong earlier, didn't I? EMPIRICAL, empirical formula. What we have to do is we're going to assume that we have 100 grams of our sample. Sorry, my light is flickering here. Okay, let's assume we have 100 grams of sample. If we have 100 grams of sample, how many grams of carbon do I have? Well, I'll have 40.92 grams of carbon. And how much hydrogen? 4.58 grams of hydrogen. And oxygen? Bring this up. We will have 54.50 grams of oxygen. Great. Now, you know what's really great about this? I can use this to calculate the number of moles I would have of each of these substances in my ascorbic acid. So that's what we're going to do. For carbon, take the molar mass of carbon, right? How are we going to find that? We're going to grab our periodic table and we're going to see, okay, carbon is 12.01 grams per mole. If that's the case, do the grams go on the bottom or the top? Well, hopefully you've been able to figure out now that the grams need to go on the bottom. And so for every 12.01 grams of carbon, I'll have 6.022 times 10 to the 23rd moles, or particles of carbon, which is 1 mole. Great. Now we can grab our handy-dandy calculator. And we can say, okay, how many moles is that? 40.92 divided by 12.01. That gives us 3.40716069 moles of carbon. Okay, obviously I've done something wrong here. Hopefully you figured it out. I need significant figures. Let's go ahead and do that right now, just real fast. And you've gotten so good at significant figures now that we can just kind of ignore that from here on out, and I'll just write the correct number of significant figures. There are 4 significant figures here, 4 significant figures here, an infinite number of significant figures here because it's exactly 1 mole, which means I need 4 in my answer. 1, 2, 3, 4. Everything after this goes away, and we'll round 1 here down, so we keep the 7. This is 3.407 moles of carbon. Excellent. Let's carry on here. Moles of hydrogen. We've got 1.01 grams of hydrogen for every 1 mole of hydrogen. And we've got 16.00 grams of oxygen for every 1 mole of oxygen. Great, we plug these into our calculator, 4.58 divided by 1.01, and we'll get, I'm going to write it over here, 4.53 moles of hydrogen. And here, 54.50 divided by 16.00 gives us 3.406 moles of oxygen. All right, so what did we do? We assumed 100 grams, which gave us really nice numbers here directly from our percentages. Then we calculated the number of moles. And now you might say, okay, I'm all done, right? We've got C 3.407, H 4.53, O 3.406. Great, perfect, all done. Except that doesn't make any sense. How can you have 0.407 atoms of carbon? How can you have 0.53 atoms of hydrogen when hydrogen is just 1 particle? It doesn't make any sense. So keep in mind that these are ratios. This is a fraction, so to speak. Except fractions only have 2 parts and this has 3 parts. So this is a ratio. So how are we going to get nice whole numbers here in our ratios? What are we going to do? Well, we're going to divide everything. We're going to divide by the smallest number of moles. And that's going to guarantee that at least one of these numbers is a 1. And that's going to make things a lot easier for us. So we're going to divide by the smallest number of moles. Great. So let's go ahead and do that now. We're going to divide everything by 3.406 moles. And we will, of course, get 1 here. And we'll get 1 here, give or take. But how about here? 4.53 divided by 3.406. That gives us 1.33. All right. So now we have a new chemical formula, new empirical formula here. Sorry, I didn't mean to have that out of view. Okay. Our new formula is C1H1.33O1. Great. Am I done? Is this it? Well, no, obviously not, right? Same problem here, this 1.33. So if my ratio is 1 to 1.33 to 1, what do I have to do to get rid of this 0.33? Any takers? I have to multiply everything by 3. So the 4th step here is going to be, if we need to, only if we need to, we can multiply to get rid of decimals. Great. So we'll multiply everything by 3. And that will give us a ratio of 3 to, I believe that's 4, but it's late where I am, and I want to make sure that I'm doing my mental math right. Yes, to 4 to 3. Now you might say, Mr. Irving, it's not 4, it's 3.99. And what I'm going to say is, yes, it's close enough. If you're within, say, about 0.15, just round. If you're within 0.15, you can just round it. Gosh, round. I swear I have a college degree. Okay. If it's within 0.15, round. Great. Most of the questions that I'm going to give you are going to be within 0.1. Great. And so we are well within that range here. And so what is our empirical formula for question 1? Our empirical formula is C3H4O3. And a really good way to test whether or not this is correct for your empirical formula is going to be, well, does this simplify? If the answer is yes, you probably did something wrong. You either didn't divide by the smallest number, or you multiplied by a number greater than what you needed to. But in our case, this does not reduce any further. And so we can say, yep, this is our empirical formula. Perfect. All right, let's go to the next question. The next question is about a particular substance called methyl benzoate. We are given a specific sample size here. Okay. We are told that we have 5.325 grams of methyl benzoate. Okay. It's found to contain 3.758 grams of carbon, 0.316 grams of hydrogen, and 1.251 grams of oxygen. We're looking for the empirical formula. Great. Now, a question like this throws a couple of red herrings at you. A red herring is when someone tries to throw you off the scent, throw you off the trail. It's when your math teachers give you information that you don't need so that you do more work than you have to, or so that you make a mistake. If we look back at our previous problem here, what was the first thing I had to do? I had to assume 100 grams in order to get out of these percentages and into nice gram numbers, which I could then use to calculate the number of moles. But in our question here, we are given a couple of things we didn't have last time. The first is that we're given a certain sample. We're given a sample size, 5.325 grams of methyl benzoate. Oh, I'm doing it again. I'm writing small. I'm sorry. .325 grams of methyl benzoate. We are also given 3.758 grams of carbon. We're given 0.316 grams of hydrogen, and we're given 1.251 grams of oxygen. So here's what I'm trying to get you to think about. Do you need to assume 100 grams? Can you assume 5.325 grams? Are you allowed to assume 100 grams? What does that even look like? And how do I get into mass percent? Do I even need to get into mass percent? Right, some of these questions that you're thinking about here. Because to do it like I did it on the previous page, I would have to first do the part over the whole times 100, right? So if in the case of carbon, it would be 3.758 divided by 5.325 times 100 to get my mass percent. And then I could assume 100 grams, and then I could get the number of grams of carbon. You don't have to do that. You don't have to do that because I already actually gave you a gram to gram to gram ratio. It's already baked into the problem. So you can see there's two red herrings here. First, I give you this sample size. Second, I don't give you the mass percent. I give you the number of grams of each thing. Okay. The goal here is to get 2 moles. So however you can do that easiest, that's what you want to do. So now having said that, I want you and your neighbor to work on this problem together. Let's do 5 minutes max. And so let's go ahead and pause the video and have you work on that right now. Okay, so hopefully you paused the video and you made it at least this far here. Once you got this far, you divided by the smallest number. And that will give you your mole to mole ratio. So my ratio here that I calculated was about 4 to 4 to 1. And so the empirical formula of methyl benzoate is going to be C4H4O. How'd you do? Bet you did pretty well. That's great. All right, so we've done a couple practice problems here. We've talked about empirical formulas. We have not yet talked about molecular formulas. So I want you to go to the next question. This is mescaline, which is a hydrocarbon made up of only hydrogen and carbon that occurs in crude oil. It's 89.92% carbon, and the molar mass of the compound is given to us as 121 grams per mole. It wants us to calculate both the empirical and the molecular formulas of this substance. So here's what I want you to do. I want you and your neighbor to go ahead and calculate here the empirical formula. And once you've done that, I will show you how to calculate the molecular formula. Go ahead and pause the video and do that now. All right, welcome back. Hopefully you have gotten this far and are able to get the empirical formula C3H4. Take a second now, double check your work. What area is the hardest for you? What area do you need the most practice in? Think about these things. Write them down so that you know what you need to focus on. Okay, so now we're going to move to the next thing, which is determining the molecular formula. Now you can remember from all the way at the beginning here, where we talked about the difference between empirical and molecular formula, where the empirical formula is the simplified version, and the molecular formula is this expanded version, the actual chemical reaction. Sorry, not reaction. The actual chemical formula. And we had some kind of number that we had to multiply that ratio by in order to determine what that molecular formula will be. And that's what we have to do now based on the information that's given to us. The only other information we're given is that the true compound, not the empirical formula of the compound, but the actual compound has a particular molar mass. The molar mass is given to us as 121 grams per mole. All right. Well, it is sometimes the case that a particular empirical formula will be the molecular formula. How would we determine whether or not that's the case here? Well, all we would have to do is we would need to go ahead and figure out the molar mass of this guy right here. We've got 3 carbons, and each carbon is 12.01 grams per mole. And we have 4 hydrogen, each of which is 1.01 grams per mole. I think you're already going to beginning to see that this is not going to equal 121 grams per mole. So we got 3 times 12.01 plus 4 times 1.01. And we're going to get 40.07 grams per mole. Right. Those of you who are particularly math-minded might see where we need to go from here. I want you to think about it. How do I know what number I need to multiply my 3-to-4 ratio by in order to get my molecular formula? Well, what we're going to do is we're going to compare this guy and this guy. And when you get a word problem in math and it says to compare something, usually that's going to mean division. Right? I'm wondering how many times does this guy go into this guy? And we can just do that by dividing, gosh, my spelling today is terrible. Dividing the molar mass of the molecular formula, by the molar mass of the empirical formula. Great. So that will be I'm sorry, it's the other way around. No, it's not. No, that's the right way. This is 121 divided by 40.07. All right, when we do that, we're going to get a number. It's usually not a whole number. And what we're going to do is we're going to say, okay, that's close enough to 3 that we know that with our 3-to-4 ratio, we have to multiply it by 3 to get our molecular formula. And that's going to give us 3 times 3 is 9, and 3 times 4 is 12. Right? So while this up here is our empirical formula, our molecular formula is C9H12. And that's our answer. Hopefully you can see it's not terribly complex, but it does really depend on a very firm understanding that this is a ratio of chemical formula, is a ratio of moles of one substance to moles of another substance. So all we're doing is we're juggling moles. That's all we're doing. Hopefully these little directions here are useful and helpful to you. All right. So let's look at the next question. The next question is about monosodium glutamate, or MSG, which is actually a really cool compound. This is a flavor enhancer in many foods, especially Asian foods, and it contains 35.51% carbon, 4.77% hydrogen, 37.85% oxygen, 8.29% nitrogen, and 13.60% sodium. And the molar mass of the compound is 169 grams per mole. I want you to calculate the molecular formula. Why don't you and a neighbor try this now? Come back to me in 5 minutes or so, and see how far you've gotten. Go ahead and pause the video now. All right, here I've calculated out the empirical formula. Hopefully this is what you got for the empirical formula. And now what I want you to do is make sure that everything here looks correct. And if it does, continue on in just a second here, and I will have all of the work necessary for the molecular formula. Go ahead and pause the video now if you haven't gotten that far yet, and I'll be right back with the molecular formula. All right, so for our empirical formula, C5H8O4NNA, we can go ahead and calculate the molar mass here. We get 169.13 grams per mole. And then you can take your significant figures, it's 169.1 grams per mole, and compare that to the molar mass that we were given. We can see that they're the same. And so that means that this is our molecular formula. All right, that ends my lesson for you today with this awful echoey sound. I hope it was useful. For the rest of class today, you're going to be practicing either individually or in groups, according to the preference of your sub. If you have any questions, my office hours are now live. Please go to our bulletin board or to the email that I sent you, and go ahead and sign up if you have any questions. I'm super happy to help out. Hope you guys are doing well. I'll see you soon. Take care.